say welcome Nuki for your PhD transfer presentation. Very much looking forward to hearing your work. So right now the floor is all yours. Thank you.
Thanks. Yeah, so my working, my working thesis title is Knowledge Distillation Method for Making Neural Machine Translation More Efficient. So yeah, I'm based in DCU in the School of Computer Science, and my supervisors are Andy Way, Reginald Hop, and Julie Brinson. I started the PhD about 2 years ago in September, October 2019. And then, yeah, I'm part of the ADAPT Center and the ML Labs cohort. So yeah, just an overview of what I will be talking about. So I'll just give a brief introduction, then go through my research questions, and then also just the related literature that I have reviewed up until now in terms of each research question, the work I've done as well, then the completion time frame, and then just a short conclusion. Yeah, so with sustainability, like nowadays especially, it's very easy to see if something is green or not, with electric cars and recycling, and then also especially like with chemistry, you get green labs. But for machine translation and AI, it's not always that clear. I mean, myself as well, like you're not always aware of the impact you're making on the environment when you're training large models, because you can't actually see, like say with factories, smoke coming out of the data centers or something like that. So yeah, we definitely need to kind of be more aware of the impact that we are making. And then just as an example, a natural language processing model with a transformer architecture, which is state of the art now, and neural architecture search, actually, like if you train a big model like that, it emits quite a lot of carbon dioxide. So yeah, as you can see there on the slide, one of these models, by using the GPUs, actually emits about 5 times more carbon than the average car will in one lifetime. So yeah, that's just kind of to point out again that we need to be aware of what we're doing. And then also just, I mean, these models are really big, and there's becoming more of a split in NLP, because like the big companies have a lot of resources and data that they can use, and to up their performance, they just add more data, train for longer. And even say in ADAPT, we have access to a lot of resources, and probably more than a lot of research centers. But yeah, we can't actually compete with any of the big companies, and independent researchers then, or smaller research centers, also find it difficult to get the type of statistics that these companies do. So yeah, my research questions then. The first question is in terms of the architecture of the student model. So how can we define a simple and small architecture suitable for parallel computing in terms of the training and inference, and that is suitable for deploying within resource constrained environments? And then the second question is in terms of the kind of knowledge that needs to be transferred or distilled. So the big teacher models then memorizes the entire data set and learns different knowledge. So we need to design an objective function to better show what knowledge we need to translate for our student models. And this can be in terms of maybe just translation, or if you're looking at the engineers using NMT toolkits, like you can also create this function in terms of hardware usage or resource constraints. And then finally, research question 3 is in terms of the balance between the model size and the performance. So we need to come up with some sort of composite evaluation metric that can state with confidence what the best balance would be between our model size and the system performance. So yeah, then for the related work, so the usual training criteria for multi-class classification can be used to develop a function for knowledge distillation. And then this can further be expanded to finally get a function for sequence level knowledge distillation. So usually if you're trying to classify a set of data into different classes, the aim is to minimize the cross entropy between the data distribution and the model distribution. And you can do this by minimizing the negative log likelihood for each training example then. So when it comes to knowledge distillation, it can easily be applied to NMT models because these models minimizes the word NLL during training. So because basically, I mean, if you have a target vocabulary, you're trying to classify your source sentences into that vocabulary. So we also then already have a model distribution that has been learned by the teacher. And then, yeah, you can easily rewrite the previous function in terms of knowledge distillation then for word level distillation. And then finally, if you're looking at sequence level knowledge distillation, the previous function then, instead of looking at words in a sentence, you'll look at whole sequences. This, however, is quite difficult actually to handle because it's very complex and there is an infinite amount of sequences that is available. But then because we have the distribution that's been learned by a teacher, we can actually just use the mode of that distribution for sequences. And I mean, there are so many sequences, but by using beam search, you can actually just approximate that mode and then finally use that function. So basically just knowledge is then distilled by generating a new training set, by translating a training set with a teacher model using beam search. So yeah, just an overview of then what sequence level knowledge distillation looks like is you train a teacher set on, say, like call it like an original training set. Then you translate this original training set to create your new training set with that's your new knowledge distilled training set, sorry. And then you use that distilled knowledge training set to train your student on. So yeah, in terms of the architecture then of our student models, so in the paper by Curry and co-authors, if you want to distill multiple domains to create a general domain student, you'd have a big teacher model that's in this case 12 encoder and decoder, that has 12 encoder and decoder layers on multiple domains. And then you fine tune that teacher model on the individual domains to create domain specific teacher models. And then finally, you translate each domain with the teacher that's specific to that domain, and then use the student to train on all those newly created training sets. And you'll have a general domain student model. But this only works well if the domains are very clearly defined. So yeah, the other paper then that is kind of important for our architecture that we use is by Gordon and co-authors. And they've also used a similar architecture where they have 12 encoder and decoder layers in the teacher model and only 6 encoder and decoder layers in the student model. So we tried to replicate some of their work, but we were unable to train these big teacher models with the Marion NMT toolkit because it just uses so much memory when these models are so big. I think after like 2 or 3 iterations, training would stop because we ran out of memory. So by trying to get this to work, we've decreased the batch size, workspace memory and validation mini batch size parameters, but then the accuracy of these models were really bad, so there was no point in really using that then. And because of that, then we just decided to focus on knowledge distillation for resource constrained environments. So yeah, in terms of the knowledge that needs to be distilled, so we did then what Gordon did in their paper to improve our student models. And you do this by training the student on the knowledge distilled training set combined with the original training set that the teacher was trained on. And this greatly improved the performance of our student models. So, and then besides this, we also plan to calculate the uncertainty scores of each sentence that was translated by the teacher models. And if you get the score for each sentence, you can then either undersample or ignore the sentences that's very uncertain and upsample the sentences that are very certain. And then hopefully, the student model will closer mimic the teacher model. So in terms of research question 3, then all of our models, like the performance, was measured using automatic evaluation methods. So blue, translation error rate, and the character F score. But these only indicate the accuracy of our translations. We need to do some more research on how we can better define the efficiency of our systems. So, and then also, we need to use human evaluations as well to see how much of a difference there actually is between translation quality. And then this question also needs to be answered in terms of the interests of let's say, like different people. Then, so from this, you need to, if you're only worried about translation accuracy, then I mean, you can see with the blue scores that the students do perform better than the teacher models, and we need to do some human evaluations then as well. But if you're looking at it in terms of hardware and resource constraints, we need to find a better balance, or we need to define a metric to decide if you only have like 1 or 2 GPUs, say, or a time limit, then is it worth actually creating these student models? And also, we can do this in terms of the amount of training data that you have, look at it in that way as well. And then also deployment needs to be taken into account here, because if you're paying for GPUs as you use them, then you definitely want something that can translate faster. And then finally, the environmental impact. We need to have a look at the amount of electricity the GPUs are using. So in the deployment phase, the student models, for example, actually translates a lot faster, but we also need to take into account that translating the original training sets actually took quite a while, and then training the student models also took a lot of time. So we have to get some figures on that. So what we've done up to now, then, all of our experiments, we use the Europol corpus and translated from German to English. The corpus was then divided into subsets. So there's about 2 million training sentences, and then 3,000 validation and test sentences each. And like I said before, we used the Marian NMT toolkit, and the architecture for our models, we used the transformer architecture, and all the models were trained up to 20 epochs. So just the table there then shows the difference between our models, where the baseline and the student models only have 3 encoder and decoder layers, and the teacher has 6 encoder and decoder layers. And the difference between the baseline model and the student models then is that the baseline was trained on the original training set, and the students, there's 2 types of student models. So they were either trained on the knowledge distilled training set, or a combination of the knowledge distilled training set and the original training set. So yeah, there's just the scores of our baseline and teacher models. And I mean, as you can expect, then training time goes down as the number of GPUs go up. And then also with the teacher models, the blue scores also go up as the number of GPUs go up. But baseline 2, there is a bit of an anomaly, since that's the best baseline model on 2 GPUs. And then the best model between our baseline and teacher models would be the teacher that was trained on 4 GPUs. You can see it has the best blue score and TR and character F. So the student models then are, like I said earlier, are similar to the baseline models, where they have 3 encoder and decoder layers, but then the training data differs. So in terms of research question 2 then, for the kind of knowledge that needs to be distilled, when we created the new knowledge distilled training sets, we used the beam size of 12. That's usually just, if you're just going to kind of, if you don't want to experiment, like 12 is a good start for beam size. But yeah, we need to experiment with that a bit more, because if you choose a smaller beam size, you can translate these sets quicker, and we need to see if that makes any difference on the performance. And yeah, so for the student models then, student model 6 there was on the Europol and knowledge distilled training sets with 4 GPUs, and that has the best blue score overall for all our models. And yeah, for some reason, yeah, the blue score went up as the GPUs went up, but the translation error rate actually just stayed the same. So we could look into that a bit more. And then also just the training times then for these types of students then are longer than the teacher training times as well. So it did score better, but only marginally, but the training time is longer. So what we've seen now from our experiments so far then, our student models only perform marginally better than the baselines actually. And the training steps and training time actually took a lot longer. So this is now what I said earlier as well at the start, is it actually worth it then to go through all this effort if it's only marginally better? So we'll have to look in if it is then worth all the computational steps. We'll have to look into that. And then also with research question 2, if we can distill knowledge better, then maybe it is worth it. So research question 3 needs to be adapted a little bit to also address this. And then yeah, for the sentences, this is between the baseline with 4 GPUs and the teachers with 4 GPUs. They do look quite different. So this is where human translators would be good for evaluation, just to kind of rank how much of a difference it actually is in fluency and adequacy. So finally then, this is some new work that I've done since I submit the report. So I've started my internship at Canton MT, and on their platform, there's some site statistics on so yeah, there's some site statistics on how many words they've translated since I think August 2018 maybe. And yeah, so I just kind of got a monthly average amount of words that they do translate then. So in the first table there, I got the time in seconds it took for the teacher and student models to translate the test sets that had about 3,000 sentences in them. And you can see that there the students take about half the amount of time than the teachers do. And then, yeah, so you can see here, so I got kind of estimates for the cost and carbon emissions then these models. So the cost, if you're using a AWS and a dynamic instance where you just pay for the usage of the GPUs, you can see that like if it's in the translation or deployment phase, using the student models, then because they're so much smaller, they translate faster. So you can see, I mean, it's almost double the amount to use the teacher model, and the emissions is also almost doubled. Now the emissions, those numbers aren't accurate, but there's a website that calculates this for you. But actually, so this all depends on the local electricity grid as well. So to get a better figure, we'd need to take this into account. But the scale between the different models is relatively accurate, because we use the same method for all of them then. So yeah, the completion time frame then. So the thesis write-up, I think I should have changed that a bit if in the report, because I am writing up as I'm going along, but probably in the final year, I will actually only start writing up the thesis. So yeah, for ML labs, there are quite a few requirements. So there's like workshops in schools that we need to attend throughout the PhD. And we started off with a 6-week boot camp in September 2019 or October. And then, yeah, so I also finished all the taught modules. So for the credits we needed for the ML labs requirements and DCU requirements. And then the industry placement. So yeah, the internship then with ContentMT is for 6 months, and I've started it a couple of weeks ago. And yeah, so the internship, actually very lucky with that. The internship is very closely aligned to my research. So the work that I'm doing there might actually feature in the thesis as well. And then what we also still need to do kind of is go through these findings again thoroughly, so we can better define research question 3, because at the moment that's still a bit of an open question now, because we're not sure if the student training these student models is worth all the hassle for a minor performance gain. Yeah, so finally, just in conclusion then, yeah, I've showed how we intend to use knowledge distillation to make NMT more efficient by defining my 3 research questions and stating how we will address them. So for research question 1, then we've shown why and how we define the architecture of our student models, but there needs to be more tests with the parameters for these models. So like, I mean, we could limit the epochs so the training is quicker. Also smaller beam size when translating from the teachers. And then for research question 2, sorry, I provided the related literature to motivate why we're using the knowledge distillation methods we are using for our experiments. But then we also still need to use the uncertainty scores, so the teacher can closer mimic, the student can closer mimic the teacher model, and maybe see if there's other ways of also improving the knowledge that's learned. And finally, for research question 3, then we've stated the variables that we need to take into account to find a good balance between accuracy and resource usage. But then we still need to derive an evaluation metric for this balance, so we can confidently say whether these students would be worth it or not. Yeah, thanks.
Okay, thank you very much, Nuki, for that very interesting presentation. It certainly is a topic I hadn't come across before, the environmental impact. Do we have any questions from the floor while we're still in the public session? You can put in the chat window, or you can unmute yourself and just speak. Anybody? I'm curious myself because my interest was piqued about the environmental impacts. So how do you foresee your research then being used by the community once you're finished?
Well, I guess so this is all it kind of revolves around research question 3.
Yes, evaluation metric, right?
Yeah. So if we can come up with an evaluation metric that can confidently say, listen, the performance isn't actually that much better. So why are you training for this long? And then, I mean, maybe it'll stop you from like doing more experiments on it.
Yeah.
Or if we can come up with better ways of creating our student models, then if you're deploying this, like that big teacher model only has to be trained once. And then the smaller student models can kind of like after they've been trained, just be fine-tuned. And they'll use a lot less GPU power than the teachers would.
Okay, no, that seems very interesting. It was also quite an eye-opener to see the amount of CO2 produced by training large models. So yeah, very, very interesting work. Very, very good. Is there any other question before we go to the private session? Last chance.
Yeah, thank you, Wandri. It's very interesting topic and very nice talk. So I think we should be concerned about this thing like carbon emission. We should save the environment. So I just have a small question. Like in your student model, you are using the knowledge distilled corpus plus Europal corpus, right?
Yeah.
Yeah. So this is, I mean, again, a large corpus, like the size of the Europal and plus the.
Yeah, so that would be 4 million sentences then.
So, I mean, just a comment, like, is it possible maybe in future we can look into the part that where you won't use the whole part of the Europal corpus, but maybe a part of it, depending upon the domain or.
Yeah, so this is with the uncertainty scores that we still need to do. If we undersample the knowledge distilled sentences or either in the Europal corpus, then there will be less sentences. But also, yeah, we did train on only the knowledge distilled set, which is just as big as the Europal set. But the improvements there weren't really worth it. So we do need to look into how we can actually use less than for Europal. Sorry, for the student models. Does that answer your question?
Yeah. Okay. Thank you so much.
Okay, I'll say last chance for a question in the public session. Otherwise, we will close the public session and stop recording. Okay, I think we're good. I think that's clear. So thank you very much for attending.